In the first episode, I will build the simplest machine learning model. I will demonstrate how it deals with numbers. For all black and white images, we can use the grid value of each pixel to represent any image. Of course, the higher the pixel, the higher the spatial dimension, and the longer the training time. In the process of the machine learning, the most important thing is that if the machine's judgment is correct, it will glow green, and if its judgment is wrong, it will glow red. If it is wrong, the 784 weights will be adjusted automatically. And this automatically adjustment is the underlying layer of the whole machine learning and the core secret of artificial intelligence. So, let's get started. In the first episode, let's learn how machines recognize numbers. So, let's start with a nimble project. Let me write a number on the left window, such as 3, and our machine learning model will judge which number you are writing. Isn't it enjoyable? Actually, developing such a function is quite simple, and in the following video, we will train a neural network that can recognize numbers. To achieve this, the first thing we do is to turn the picture into a number so that our machine can use it to learn. This is a database called MList, which contains 70,000 pictures, each of which is a 100 number. All the pictures are pre-processed and they are 28 by 28 pixels. In other words, there are 784 small squares that make up this number. There are 28 in each row, a total of 28 rows. But only one message in each square, grayscale. You can think of grayscale as light or shade information. Today, we usually use 8 bits, 8 zeros or ones, to store the grayscale of each pixels. In combination, there are 256 total possibilities. When the grayscale is equal to 0, this square is pure black. When the grayscale is equal to 255, this square is pure white. Between 0 and 255, it is gray from light to dark. Let me drag the vertical bar to adjust the color of this square. In theory, I can adjust the value of pixels, each of the 784 squares, until I reach a number 3 that can be recognized by the machine. But to make it easier for me to demonstrate, I simplify the square from 28 times 28 to 7 times 7. Now, let's adjust this 3 to 7. By adjusting the value of each pixel, we can represent a picture with 784 numbers corresponding to 784 squares. Taking the number 3 as an example, we record grayscale values of these 784 pixels from the pixels in the upper left corner. x1 equals 0, x2 equals 0, x3 equals 0, x4 equals 0, blah, 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 blah. I won't finish reading them one by one. Let's skip to the end. The resulting 784 xi can form a vector. Let me explain vector. Vector has multiple understandings in mathematics, but in our machine learning project, you can understand the vector as a point defined in the coordinate system. If this is a one-dimensional vector space, 3 is here. In a two-dimensional vector space, 3, 5 is here. In a three-dimensional vector space, 3, 5, 7 is here. The vector we just got from the picture with 784 numbers is a point in the 784-dimensional coordinate system. But I can't show you what the 784-dimensional coordinate system looks like. In the following content, I will further explain the dimensional problems to you. Okay, how should our machine distinguish between these different numbers in handwriting? Let me take 3 and 7 as an example. There's a left protruding part in the middle of 3. So, in the vector of the number 3, the pixel grayscale in places like x350 and x378 is usually higher. But these pixels are blank in the number 7, the grayscale will be relatively low. On the other hand, on the pixels in the low middle area, such as x713 or x740, the grayscale of number 7s is generally higher. So, after we point the vectors that represent these two numbers to the 784-dimensional coordinate system, the vector of number 3 will form a set, while the vector of number 7 will form another set. What we need to do next is easy. We can ask the machine to draw a line to separate 3 from 7. In a two-dimensional space, with a one-dimensional straight line, we can divide it into two parts. In three-dimensional space, we need a two-dimensional plane to divide it into two pieces. In our 784-dimensional space, we need a 783-dimensional hyperplane to completely separate it. Expressed by the perceptron formula, it is W1 times x1 plus W2 times x2 plus W3 times x3 plus W4 times x4 blah 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 plus W784 times x784 plus b equals 0. The 784 x's here are the grayscale values of 784 pixels. Each pixel has its own weight W. Adjusting the weight W and threshold B can change the position of the split line. So our goal is to get the machine to change W automatically to separate 3 and 7 as accurately as possible, to divide 3 and 7 into two categories in 784 dimensions. This is what it looks like by chart. Let's multiply the gray value of each pixel by the corresponding weight W, and then add them. If it is greater than the threshold B, the machine judges that it is 3. If it is less than B, the machine judges that it is 7. Okay, then we can get the machine to train itself automatically. To give you a more intuitive understanding of what happened in this process, I developed a visual 3D model. These 784 squares are the 784 pixels in each picture. A line attached on each grid represents the weight. If the weight is 0, the light is transparent. If the weight is negative, the line is blue. If the weight is positive, then the line appears orange. The 784 lines are connected to this output point. If our machine's judgment is right, it will glow green. If its judgment is wrong, it will glow red. If it is wrong, the 784 weights will be adjusted automatically. As a result, the color of the line will change. This is the iteration in the upper left corner. We mark the number of iterations of real-time changes. Okay, now let me adjust my perspective and demonstrate the training process. You should pay attention to the observation. What is happening in the picture now is the process of training neural network. Training a reliable model requires a lot of data. This time, we use 6,131 pictures of number 3 and 6,265 number 7 pictures in the MNIST database. We store these 12,388 pictures in advance. Then we set up a neural network structure. In the upper left corner, you can see our training progress. Okay, I think it's almost done. Now let's use the model we have trained to enter the test phase to see how accurate it is. Next, I will take turns inputting another 1821 images from the MNIST database into this model I have just trained to see how accurately it is. The accuracy is only 75%. If we have patiently trained all the data, the result would have been much better. So let's do it again. Retrain the machine again. Now, all we have to do is to wait. This process is called training neural networks. In this case, the neural network is the 784 lines representing the weight W, as well as the threshold B each time I input a picture. I multiply the grayscale value of each pixel by its corresponding weight W, and then compare it with threshold B. If it is greater than threshold B, the machine will judge it to be 3. If it is less than B, the machine will judge it to be 7. At first, the machine is bound to make a lot of mistakes. But machine learns. Whenever the judgment is wrong, it adjusts weight and threshold according to a rule. You can also see it in the middle of upper right-hand corner. In fact, the pattern of weight is changing all the time. Thank you for watching my whole training process patiently. Machine learning in the real world is similar, which requires your patience and waiting. Generally speaking, the longer the training time, the better the effect. In the next episode, I will use a classification example in two-dimensional space to explain to you how machine adjusts itself.